Okay, then I will start. Yeah. So welcome everybody to the second lecture of differential geometry. So today first, I want to start with a small correction. What I did not realize yesterday, I made a small typo. So if you remember when I was explaining the Taylor series expansion of the single variable. So if you remember, if gamma was a unit speed curve, so I expanded gamma t plus delta t minus gamma t. This is gamma prime t plus half gamma double prime t delta t square plus higher order terms. So this somehow I did not check carefully. This I actually wrote gamma double prime. So that doesn't make sense because later, of course, I used gamma dot with the unit normal. This was perpendicular to the unit normal, so this was 0. So this was heavily used actually. So I just wanted to make sure that this is in everybody's mind. I mean, this I have also corrected in the lecture notes. So I hope this would be okay. Yeah. Good. So then let me just recall what we have learned last time. So let S be a surface and P be a point. Then we have constructed a map, Gauss map, from S to S2, sending P to the unit normal at P. After this, we have also defined a Weingarten map WP at S as minus dpg. This was a map from the tangent plane at P of S to TPS. And the final thing what I defined yesterday was the second fundamental form was given by the bilinear form VW at PS as the inner product given by WPSV, WPS, where you have V and W are element in the tangent. Okay, this was defined yesterday. So one thing again, or like kind of a warning. So you would see in the book also, this is also defined as an inner product or like a bilinear form. And here it's also inner product. Now this one, how do you define this? So WPS of V, that's an element in TPS. And W is also an element of TPS. So then, since this is a linear map, there you already have a well-defined inner product actually. That's kind of obvious. But this inner product, so V, so let me remark this actually. Careful about the notation. Because sometimes what can happen, this VW, this might be either we are thinking about inner product directly like a previous definition, like a normal dot product, or we can also think as taking with the Weingarten map. Okay, so one has to be careful what we are meaning. But anyway, so what today we will start with a lemma that I already stated inside the definition. Lemma. So what did I say? That this VWPS, this is a bilinear form. So you have to prove that this defines a bilinear. Okay. And yes, just let me repeat. Please stop me if there is anything unclear. Please do not hesitate. Okay, so this I already said in the definition that this is a bilinear form defined by this. But just let's check for sanity that this actually defines a bilinear form. So what do I mean by this? So let's let me say what do I need to check for bilinearity. So I need to show that lambda 1 v1 plus lambda 2 v2 w. This I have to show. This I have to show that this is lambda 1 vw plus lambda 2. Sorry. v1w v2w. Right? So if I can show this, then this is bilinear. So this, let's go with the definition. So what's this? This is nothing but the Weingarten map W of lambda v1 plus lambda 2 v2 of W. And this is now W was a linear map from the tangent plane to tangent plane. So this actually decomposes. So this becomes lambda 1 W v1 W plus lambda 2 v2 W. And then you just use the bilinear. Here you also use the bilinearity of the inner product, and now you use the linearity of W. So this becomes then nothing but V1. So it's just matter of checking. So we are done essentially. So here what did I use? So I use linearity of W and bilinearity of the inner product. Now again, let me again stress this. By this inner product, I am talking about the right hand side inner product, not this one. This one I have to check that this is bilinear, so I can't use that this is already bilinear, right? So I hope the distinguish or the difference is clear. Good. So that's nice. So what we said in the definition, it makes sense. And now the next obvious question is, here I am saying this also to be second fundamental form. But if you recall from yesterday's talk, I have also defined second fundamental form in terms of second derivative. There was an expression, right? So with L, M, and N, so I somehow has to show that they define the same same second fundamental form, and that's what I promised yesterday in my first part of the talk, right? Whatever approach I take, somehow every approach will lead to the same concept or like the same second fundamental form. So what should I show? So that's the content of kind of we are going towards the next proposition, where we will show that this definition also lead us to the same second fundamental form as we did yesterday. But first, let's build some preliminary lemma which would help us in the calculation. So let sigma UV be a surface patch with standard normal in UV. Then you have some set series of relations like NU dot sigma U is actually minus L. NU dot sigma V is NV dot sigma U is minus M, and NV dot sigma V is minus N. So what are this L, M, and N? So L is essentially sigma UU dot N. M is sigma UV dot N, and N is sigma VV dot the not unit normal. Yeah, that was our definition in the second fundamental form. So what I'm saying is, if you take the dot product with NU dot sigma U, you get the essentially the first coefficient of the second fundamental form in the negation. And similarly as this. Okay. Right. So let's prove this. It's not difficult. It's just a matter of writing things down. So you know that as sigma U and sigma V both are tangent vectors. So both are tangent vectors to the surface patch. Right? So what does this give you? That N with the unit normal, if you take dot product, this is 0, which is also same as N dot product sigma V. Right? This is by definition, since these are tangents, so these are perpendicular to the unit normal. But that's nice because now I differentiate these two equations with respect to U and V. Then from the first, what you get is NU dot sigma U plus N is like the normal. Here again, I'm sorry for the confusing notation, which without bold N and N, that's a bad notation, but since it's going on for a long time, I can't change it. With 0, so that means NU dot sigma U is minus N sigma UU, and that's the L. So this is minus L. And similarly, NV dot sigma U is minus N dot sigma UV is minus M. And once you differentiate with N dot sigma V, you get minus N dot sigma UV is minus M, and the other part is NV dot sigma V is minus N dot sigma VV is minus M. Right? This is, I mean, you just understand one thing, right? This you are differentiate with, let's say first with respect to U, then you get by chain rule, and then just taking this coefficient to the other side, and then you get this. And similarly, you get also minus m. This again you get because uv, these are kind of symmetric, so this you get here. And the finally you get for nv dot sigma. Okay. So this is nice. And this you are going to see how it is being used in the main kind of proposition. So that's the next proposition. So let P be a point of a surface S, and let sigma uv be a surface patch with P in its image, and let L du square plus 2m du dv plus n dv square, this be the second fundamental form defined yesterday. Then you can show that for any VW in the tangent plane, you get the second fundamental form defined today, VW. This is actually L duv plus, sorry, L duv duw plus m du. Let me write it in the next line. It will be easier. So the inner product, this is equal to L du v du w plus m du v dv w plus du w dv v plus n dv v dv w. So what I'm saying is, so once you have these coefficients L, M, and N, this right hand side, this whole big expression, this actually defines a bilinear form. This, there was an exercise also before. I mean, even in the first fundamental form, when you have a form like this, then you can formulate a bilinear form in this way. So the content of this proposition is saying the bilinear form defined in this way, along with the Weingarten map, this bilinear form and the bilinear form given from the second fundamental form from yesterday, both are the same bilinear form. So essentially what I'm saying is, then both definition lead to the same definition of second fundamental form, or in other words, both have the same content or same amount of information of the curve. Okay, is this clear? I mean, what I'm saying?
Yes, sir.
Okay. So, I mean, the conclusion of this proposition or the content, what you should take home is both the definitions, they carry the same information. Okay. So now, how should we prove this? I mean, just let me just remark this. So, i.e., both definition gives the same information. So let's try to prove this. So how should we prove? So here there is a bilinear form, and here there is another bilinear form. So it's a basic exercise in linear algebra, that once you have two bilinear form, then how should we, I mean, if it's a bilinear form, like in every variable it's a linear, then how do you prove it? So essentially you don't need to prove for all vectors in the plane, right? I mean, remember little bit about linear algebra. So the basic technique was to only consider on the basis vectors, right? Then it's enough. And that's exactly what we do. So note, both sides are bilinear forms on the tangent plane. So enough to verify the equality on the basis, right? And we have a favorite basis here we can take, which we will take as V equal to sigma U and W is sigma V, which is a basis of TPS at this. Now, if we take this as V and W, then immediately you see the du of sigma U, this is dV of sigma V. Any guess what is this? So du of sigma U, what's the value? What will be? What is it going to be? Any guesses? And similarly, I'm going to ask du of sigma V and dV of sigma U. Any guesses?
1 and 0.
Yes, 1 and 0. Okay, so that's very nice, because now if you put V and W, instead of V and W, if you put sigma U and sigma V, and you put on this long expression, yeah, then it's immediate to reduce actually. So essentially we have to show that sigma U, this is L, sigma U, sigma V, which is same as sigma V, sigma U is M, and sigma V is M. Right? I mean, you just you put, instead of V and W, you put sigma U. Then you see here, this is 1 and everything rest vanishes. So then you get L, and if you put sigma U, sigma V, then you get only M, and if you put sigma V, then it's, so that's enough, because, and that, since that's a basis, so you get the linear combination and you are done. Okay, so essentially now we will only see why this is true, and the rest are essentially similar. Okay, good. So let's see how this is going to be the case. This is also kind of almost from the definition. So now we know that P is in image. So let's assume that there exists a parameter U0, V0, such that it's P. Then let's compute the Weingarten map of sigma U. So this is by definition d by du at P, right? If you remember. So this is at U equal to U0 of the Gauss map of U0. Now, what was the Gauss map? So Gauss map was essentially the unit normal vector at that point. So this will be NU V naught. Okay. And then if you differentiate this, this is nothing but actually NU. Sorry, minus N. Okay, so let me again recall where N, this N is the bold N. Is the standard unit normal sigma. Okay, similarly, you can also compute W of sigma V is minus NV, and similarly go. Now let's compute what's sigma U, sigma U. So that's by definition W of sigma U, sigma U. And then that's again, if you now put this calculation, so this is nothing but minus NU dot sigma U. And now if you remember this previous lemma, yeah, here. So NU dot sigma U, this is minus N. So now you just put that. So minus NU dot sigma U, this is N. And that's exactly what I needed to prove. Sigma U dot sigma U, it's N. Okay, so the rest you can compute as a similar exercise. So rest similar. Okay, so let's again come back to the main statement. So essentially what we obtained is the inner product given by VW is the same as essentially inner product given by the second fundamental form or the coefficients of the second fundamental form given yesterday. So essentially both the definitions carry the same information. Okay, but this is also not only nice, I mean, of course, then we are kind of coherent in both the definitions, but it also gives a very nice corollary, which will be very important in the next lectures. So as a corollary, so we already know the second fundamental form is a bilinear form that we proved already, and also we saw in the proof. I mean, we used that in the proof. So the second, but that's not only a normal bilinear form. I mean, it has some even nicer property. It's a symmetric bilinear form. So the second fundamental form is a symmetric bilinear form. Or equivalently, how did we define the second fundamental form in this way? So this was the inner product between the Weingarten map and some other vector W. So when that inner product is symmetric, that means equivalently the Weingarten map. So the spell it out. So equivalently, the Weingarten map, this is self-adjoint. So it's the same definition. The notion of self-adjoint is actually given by the symmetric bilinearity property. So that's essentially exactly the same thing I'm saying. And why this is true? Because you now have an expression of VW, and you can see that this is actually unchanged if we interchange V and W. So that's almost immediate from the expression. So see, if you interchange V and W, then this expression doesn't change. And if you interchange V and W, here this doesn't change because it's the sum of these alternating things. And if you again interchange V and W, this doesn't change. So essentially the whole sum is the same. And then this is the same, right? So it's an immediate corollary. And since the Weingarten map, it's a linear map. I mean, recall the Weingarten map was a map from TPS to TPS. So this was actually a linear map, right? And what I'm saying is this map is self-adjoint. And in linear algebra, we learned if there is a self-adjoint linear map, it has some nice properties for eigenvalues and eigenvectors. And these things we are going to use later. It's not immediate. I mean, we'll see some different geometrical properties of the second fundamental forms or curvatures. And there we are going to use the self-adjointness property and also the symmetric. Right. So any questions? So this would complete the section on second fundamental form via this way, via this inner product with Weingarten. So before I go to the next section, let me ask again if there is any question. Okay. So I guess I will assume then you have understood everything. So then let me come to the next section. So which is called normal curvatures. So as I said, the first thing in yesterday's talk and again in today's also, we are going to define kind of or like try to define curvature in a different way and somehow hope that every definition will lead to the same definition. So in that venture, we have already been successful. We have defined how, like we have understood how the curve varies or like how the curve is shaped in on the surface or like how the so all the curvature things we have defined in two different ways and both gave the same definition. Now in this section we are going to see yet another way of how to define curvature of a surface. So now first here also observe that shape of a surface, like how the surface is shaped, this is actually related to the curvature of curves on that surface. So what do I mean by this? So let me give an example. So for example, if you take a curve on a plane, then this curve can have zero curvature everywhere. Right? I mean, so here I am talking about this curvature. I am talking about this is a curvature of a curve. And if you consider a curve in a plane, then that curve has zero, it can have zero curvature everywhere. Whereas if you take, but if you take a curve on a sphere, then it's not true, right? Because you can't, there can't be any segment of a line on a sphere. So if you consider a curve on a sphere, then it can't have a zero curvature everywhere. So what I am trying to see, or what I am trying to motivate is like how the surface is shaped that has a relation with the curvature of curves on the curve. So in other words, if we can measure how the curvature of curves are varying, then maybe also we can get something about the shape of the surface, or in other words, we can maybe measure the curvature of the surface. So you see what are we trying to do? So when we are trying to measure the curvature of a surface, we are essentially approaching the same thing in a many different ways. So initially we went through the tangent plane, then we went through the normal unit vector, how that varies. And now we are seeing like if the curve on the surface, how the curvature of that curves are varying. Okay, so now let me be more precise. So let me finish. So let me finish with this. So interestingly, this should also lead to same definition of second fundamental form. Okay, so now let me be a little bit more precise. So first, let me try to draw a picture. So let's consider this to be a surface. And consider this to be a gamma inside the surface. And let this be gamma dot, which is a unit vector, like a tangent vector to S. And consider this to be n cross gamma dot. You also consider n, and then consider the gamma dot. So you complete here, and then the magnitude of this gamma dot, or like the diagonal, this actually gives you the curvature of this curve, right? This was norm of gamma dot, which we also saw actually yesterday. And this is the surface. That's kind of the, let's say, the tangent. So let me say what we are considering. So consider gamma. First, let's assume it's a unit speed curve on an oriented surface S. And gamma dot is a unit vector, as I said already. So essentially, it's a tangent vector to S. And let me continue here. So since gamma dot, we are considering here, that's a tangent vector. And if we consider like this unit normal n, this is also, n is a perpendicular to gamma dot, right? So what I'm trying to say is gamma dot, this is perpendicular to n, right? So that's nice, because then this implies gamma dot, you consider the unit normal n, and you consider the cross product n cross gamma dot. These all are mutually perpendicular to each other. Let's think a bit about this for a second. So what I'm saying, you are considering here gamma dot. By definition, n is also perpendicular to gamma dot. And then you are considering gamma dot cross n, that also by definition perpendicular to both of these, right? So then what I'm saying is gamma dot n and n cross gamma dot, they are mutually perpendicular to each other. So now essentially we have covered R3. Now we will consider gamma dot. So what I'm saying is, furthermore, gamma is assumed to be unit speed. So that means what? Gamma dot dot, this is actually perpendicular to gamma dot. Now, if gamma dot dot, if it is perpendicular to gamma dot, then what? It has to be in the plane generated by n and n dot gamma, n cross gamma dot, because these three are mutually perpendicular to each other. And if this is perpendicular to also gamma dot, then it has to be in the plane generated by n. So in other words, this implies that gamma dot dot, this will be a linear combination of n and n cross gamma dot. So let me write this down. So gamma dot dot, this will be, let's say, kn n plus kg n cross gamma dot. So again, let me write this down then. So what I'm saying here, this component, you would get kn, and in this component, you get kg. So you are getting a linear combination of gamma dot in terms of n and n cross gamma dot. Right? This is just from the geometry. I mean, it's not much complicated. I mean, just all by definition. But this is very nice, because now what you obtain, you get a linear combination of gamma dot double dot in terms of n and n cross gamma dot, and you get two coefficients, kn, like a kappa n and kappa g, and I have given the names in this manner because that gives us the next definition. So the scalars kappa n and kappa g are called normal curvature and geodesic curvature respectively. This is normal curvature and this is geodesic curvature. So essentially kn is your normal curvature and kg, g for geodesic, kg is for geodesic curvature. We will be actually not so much bothered about geodesic curvature. Most of the important things we will consider are about normal curvature. But since you get this as a free, right? I mean, as a free definition. I mean, since this is a linear combination, you get for the n component, you get kn, that's the normal curvature. And for this n cross gamma dot component, you get kg, that's the geodesic. And what do I mean by this component? So what I am trying to say is, let me remark this, which we will see in the next proposition even. So remark. So essentially, the normal curvature at a point in the surface is given by the projection of gamma double dot onto the component of the normal vector, onto the normal vector n. Let me show you the picture again. I mean, so this is the n vector and gamma dot. So you are essentially kind of taking the projection to this. That's why I completed this square. And once you project to this component, then you get kg. But we can make it even more precise. So let me formulate this as a proposition. So with all the previous notations, with previous notations, we have some very nice relations. So the kappa n, this is nothing but gamma dot, you take dot product with n. Kappa g is nothing but you take gamma dot and dot product with n cross gamma. Right? Moreover, kappa square is actually kappa n square plus kappa g square. This kappa is the curvature of the curve. And kappa n is then given by kappa cos psi, and kappa g is given by plus minus kappa sin psi. So let me write this down, where kappa is the curvature of gamma and psi is the angle between n and the principal normal small n of gamma. So when you have a curve, then also you have a small n, right? That's the principal normal. I mean, you take just the t prime t divided by norm t. I mean, if t is the tangent vector, you have defined this already in, I mean, we have also used this in the motivation for the curve. And so this n and this small n, so then essentially you get it from here. Okay, so this remark, what I was saying, if you take the projection onto the component of normal vector n, this is the normal curvature. That's exactly this statement, what I'm saying. Similarly, you get also the geodesic, but as I am saying, I'm not that much interested in this. But you get also some nice relations, like k square is kn square plus kg squared, and kn is even given by k cos psi. So essentially the normal curvature you are getting from the curvature of the curve, what I was trying to motivate in the initial part of this section when we started. So how do we prove this? So proof. So let's recall what do we have by definition. Gamma dot dot is kappa n n plus kappa g n cross gamma dot. And we know that n and n cross gamma dot, they are perpendicular unit vectors. So it's like immediate right now, right? I mean, what do you have to do? So you just take gamma dot and then dot product with n. And this would give kn, right? The rest will vanish. And n dot n is 1 because n is unit vector. And similarly, you get gamma dot n cross dot is nothing but kg. Correct? So this is the first line of this equation. Okay. And how do we get then k square equal to kn square plus? How do we get this? Any idea? So this is again, so the expression of kappa square is k, so kn square plus kg square, again follows from definition actually. Because what is kappa square? It's like gamma dot square. It's like inner product with gamma dot and gamma dot. And then you, what I'm saying is you take inner product with this, with itself. But then n dot this will be 0 and n cross gamma dot n will be 0. So essentially you get kn square plus kg square. Is it okay? I mean the proof. So
Yes, sir.
let me, yeah, sorry.
Yes, sir.
Okay, yeah. It's like the just normal vector calculation, right? I mean, you just take inner product of, let me write this down. So k square is essentially gamma, and then dot again kn. Right? And this now, if you expand this out along with the property that these are perpendicular unit vectors, then this is kn squared plus kg squared. Okay. Good. So we are done also for this one. So the only thing left is to prove this one. And how do we prove this? This is also not so difficult. So observe that gamma dot dot, by definition, this is actually k times some unit normal n. This n is like our principal normal n for gamma, for the curve, not this capital. Right? This is again by definition. But that's very nice because if this is the case, then this by definition of the, sorry, let me again show you. So this is psi. Psi is exactly the angle between n and this small n. So now you put, instead of gamma dot dot, you just put that value and take the dot product, and then you get this expression. It's as simple as that. So this implies kn is k cos psi, and this would actually imply kg is plus minus kappa sine psi, because kn square plus kg square is k square. This we have already said. So we are done then. Yeah. So essentially what we obtained is the full formula. Like this also we obtained, and all these relations were. So let me just remark here. Here in the definition, you have to remember we assume that gamma to be unit speed. So if gamma is still assumed to be regular, that we have to assume, but not unit speed, then there is no worry. Then you just take a unit need parameterization. This you have seen that if it's a regular curve, then there exists a unit speed parameterization. Then one considers a unit speed parameterization. And so if that is the case, then what you are saying essentially that Kn is actually well defined for a regular curve. You don't need to assume the unit speedness. Unfortunately, the Kg, this is actually well defined also for the regular curve, but up to sine. Because you see, I mean, here what happens, you have this plus minus k sine phi. So there will be a sign ambiguity. But that's okay. You can determine the sign along with the, so if you consider, for example, sine curvature, then maybe you can remove the ambiguity. But here we are only considering. So anyway, so what the conclusion is, if you consider a regular curve even without the unit speed, then also you can define a normal curvature. So let me just finish with the statement with the proposition, which will start next lecture, I guess, which is day after tomorrow. So the next proposition, which is very important, which will again show us that this normal curvature also gives us the same second fundamental. So what does it say? That if gamma is a unit speed curve on an oriented surface S, then its normal curvature is given by kappa n as the inner product gamma dot, which was the inner product given by the Weingarten method. Okay, so essentially what I'm saying is sigma is a surface patch of S, and sigma and gamma t is a curve, sigma ut vt is a curve in sigma. Then kappa n is actually given by L u dot square plus 2m u dot v dot plus n v dot square. So now you see this form, right? This is the second fundamental form again, as we defined even in the first lecture, which we then proved today that this is same as the giving as this form. In fact, that's the proof actually, that if you get this, then this gives actually this. So the main idea would be to prove this one, which we'll do in the next lecture. Yeah, so I'll stop here. Please ask me if there are any questions or comments.